welcome to Ladyada.
Hey everybody, it's me, Ladyada. We've got a Monday night, I think it's Monday, right? Monday night Desk of Ladyada here at Hacker O'Clock, which I guess is almost 10 o'clock. We just got back from a long weekend visiting family, so we were out of town this weekend. That's okay, we're going to do a quick and eventful Desk of Ladyada now that we are back in town. Mr. Ladyada was with me on camera control.
Hello.
Hello, do you have any updates or news? You want to jump right in?
No, we're going to just jump right in. We'll be on show and tell this Wednesday, 7:30 p.m. Eastern Time. And also Ask an Engineer tonight. We just shifted Desk of Ladyada one day so we could try to do this in the same location. Not trying to do it from a
hotel room, not so
yeah, good. So, you know it goes. All right, so take it away, Ladyada.
Okay. So I did get a couple things done right before we got on a train. So let's go to the overhead real fast. I can show my power monitoring kit. So I've got here, here's another one. Here's the TFT ESP32-S2 Feather. I actually ordered the PCBs for this design and then realized that I'd made a mistake. And I did order a stencil, but it was like I really wanted to fix the mistake. So I just reordered the PCBs, and I'm going to have to get a new stencil, and that's okay. But what happened is I have a regulator that powers the external I2C connection, so you can power and depower it. You can power it on when you want the I2C enabled, and depower it when you want to go into deep sleep mode. So I thought it'd be great for you plug in sensors like this PM2.5 or this OLED. And you only power it when you need to, and you don't need to power it, you disable the regulator. The mistake I made, though, is I forgot to connect the pull-up resistors to the same regulator. And the reason I didn't do that is because there is an onboard battery monitor. And I was like, oh, well, maybe you'd want to read the battery monitor even if the I2C is off. Problem is that when you did plug something into I2C, there would be a little bit of reverse leakage current. Not a lot, but it's almost a milliamp, and it was kind of a downer. And I was like, I really want to fix this. So I did fix it in this version, which we've got here, and it's running a little test right now. Every second it turns on, and I know it's on because it turns on the white NeoPixel. And you can also see the PM2.5 turns on, and this OLED turns on, and then it goes into a cycle of 1 second of power, like full power, 1 second of a light sleep. That's a sleep that you can restore state out of, so it's not super deep. It's just enough that it's you're saving a lot of power. The ESP32-S2 isn't running, the I2C isn't on, the NeoPixels on, but you can jump back into your program state with whatever settings you have. You do have to reconnect Wi-Fi, but you're at least not beginning from the beginning of your program. You have all your state and your memory. And then a deep sleep where you're at minimal power, but to get out of it, you have to perform a hard reset, so you do start over again. And we've used that super deep sleep state on the ESP32-S2 with the mag tag. That's how you can have it run for a month, every day, turning on, getting the weather, or getting a joke from Reddit, and then going back to sleep for a full day and being able to last a month on a fairly small battery. So let's look at the PPK. I'm using a PPK to run this. This is the Nordic PPK. It's the power monitor, which is a great power monitor. One thing I really like about this power monitor, it's small. I mean, I like the Monsoon. Don't get me wrong, it's a very high quality power monitor, but having to get the Monsoon out, it's kind of like it's on the desk and then the power supply. I mean, it's a much bigger thing. This is straightforward, but not as expensive. Maybe doesn't do as much stuff with power supply modeling, but it works great. I just made a little power cable here that connects from the control output and plugs it into the battery, and I just have it simulate a 3.7 volt power supply. So let's go to the computer. Turn on live view. So you can see here, it's, it turns on. You can see the power supply kicking in. To start up the fan on the PM2.5 and charge up the OLED, there's this huge spike to 100 milliamp as you're charging up the capacitors, you're charging up the power supply, you're spinning up the motor. And then it gets down to, running about, maybe 40 milliamps or so, maybe 20 milliamps of run. That's not with Wi-Fi. That's just like, kind of just doing some basic Arduino stuff. And this is a light sleep. So this is a sleep where it's, 1 milliamp or so, maybe 1.5 milliamps. Again, you can restore state. And then down here you see the deep sleep. So it's 80 microamps, which is pretty good. Considering I think the ESP32-S2 has, quiescent of like maybe 30 or 40. And then there's 2 regulators, and there's also like 20 microamps a piece, something, whatever, 80 microamps. Basically under 100 microamps, which is, in my opinion, very, very good. You're gonna be happy with that. Less than a tenth of a milliamp, you'll be able to run for a long time. And this is without a lot of low power engineering. I'm not using a special low quiescent power LDO because I can't get it. So I'm just using kind of a standard AP 2112. But I'm very happy with it. So I'm, reordering the PCBs, and I'm happy enough with this that I feel like, okay, I can, release this into the wild now. So that's good. All right. So any questions before I move on to the next thing?
Keep going.
Okay. So the next thing is I was working on a feather, and you came up with a name for it. It's called the Scorpio.
Scorpio is probably going to be the name.
Yeah, so this is a RP2040 board that is very PIO focused. And the goal of this board is to be able to drive 8 addressable LEDs with high-speed PIO, because that's kind of like the thing that the RP2040 does, and take advantage of all that RAM that the RP2040 has, so you can like do massive DMA buffers. And it also happily does it, in a PIO. I think you don't even need a timer. Maybe you need like one timer for like all 8, which is wonderful. And the DMA is all handled internally in the PIO structure. So this is the board. Let's look at the top traces. So here I've got, it's basically the RP2040 Feather without the SWD connector, because like, nobody really ended up using it. I put it on there because I was like, oh, people are going to debug. And it turns out kind of like people didn't really do the debugger much. They were happy to use CircuitPython or Arduino, which is not debugger friendly. So you've got the power supply and USB and battery. The crystal regulator, battery charger for the RP2040 chip. Here's the boot chip. There's a vertical I2C, so you can, like the TFT ESP32-S2 Feather, you can plug in I2C. I got the diode in here, so you can use the boot button as a user button. And what's interesting is actually like every GPIO gets used, because to do the 8 addressable NeoPixel strands all at once with PIO, the pins have to be consecutive. Like you can't have it be like PIO like 1, pin 1, then pin 4, pin 6, and pin 10. It has to be like 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't have to be on a byte boundary, so it doesn't have to start with 0 or 8 or 16 or 24 on the GPIO map, but it does have to be consecutive. And given that I wanted to make sure that these GPIO pins, like 5, 6, 9, 10, 11, 12, 13, were the true GPIO pins, because as I found out, like when we first started doing RP2040 stuff, I thought there would be more pin remapping because I'm really into pin remapping. Turns out nobody else is into pin remapping except for me. And so I have to kind of back off from doing all the pin remapping stuff. So I wanted to make sure that like pin 5 is really pin 5 and pin 4 is pin 4. And, these analog pins are analog pins, but 25 and 24 are like the real pins. So everything got kind of tight, but here is the level shifter, and I even stuck some very small series resistors just to kind of reduce any ringing from long strands of wire that could, early NeoPixels could get damaged if you had a spiky power supply and you didn't have a little bit of resistance in there to keep the keep it from the inductance of the wire from creating a little bit of a spike. So there's a little bit of resistance there, and then there's the 2x8 header at the end here with 8 outputs and 8 grounds to match. So that's the That's the design. And then Phil, Mr. Ladyada, came up with the name Scorpio. Because I don't try to ruin it. Why it's called Scorpio?
Well, we'll in some future shows we'll go into how we find some of these names, but
maybe hint. It's like this part.
Yeah, PIL maybe.
Okay, cool. So that's the design. Any questions about the design?
No. Well, do you want to generally just say what PIO is for people?
Oh, PIO is this. It's a programmable state machine that runs within the RP2040 that's dynamically reprogrammable. So you can get assembler speed data bit banging, but dynamically and in even fast. It's like faster than assembly because you can push things out in one cycle. And all the demos you've seen with like HDMI or Ethernet being bit banged on the RP2040, it's all done with the PIO peripheral, which is it was basically a hack so that you didn't. There's a lot of peripherals that weren't included on the RP2040, like I2S. Instead, they're like, here's how you implement I2S or PDM with a PIO state machine, and there's 8 of them.
Okay. All right. Do you have a great search for this week?
Yes. So let's go into the great search.
Okay,
It's going to be this little guy.
Where in the world is that part I need? The great search with DigiKey.
The Great Search brought to you by Adafruit and DigiKey, where Ladyada uses all of her powers of engineering every week to show you how to find the things in the world on digikey.com. Perhaps the biggest, best place to get electronic components in the world, we think anyways. Anywho, Ladyada, what is this week's Great Search?
Okay, so this week's Great Search is while I was designing, whatever I was designing, that's kind of what makes it into the Great Search. Because I was like, I'm actually searching for this and I should do it. This week's Great Search is a 8-channel buffer transceiver, non-inverting, that I added onto the SCORPIO Feather that will convert 3-volt, 1 megahertz signals, so fairly fast signals, from about 3.3 volts safely up to 5 volts. That's the 5-volt signal comes from the USB line. The microcontroller runs on 3.3. I want the output to be 5 volts. I can't run the microcontroller at 5 volts. I run the microcontroller at 3 volts. I output the signal and I buffer it up and out into a pretty 5-volt level signal. And I want a 8-channel buffer that does this nicely and cleanly. So let's go to the computer.
All right.
Okay, so this is my schematic. These are my signals coming in, 8 signals. I'm using, there's actually a couple chips that do 8-channel. There's like literally buffers. This is technically a transceiver, the 74HC245. And most importantly is I need it to be really small. Sometimes, for example, if I, let me just for fun's sake, I'll show the TSOP. The TSOP would not have fit. So this would be the TSOP version. And, I'm already using 0402 resistors. There was no space. I had to go down to a QDFN. And thankfully there are QDFNs of 74 series logic. But I never showed, I talked a little bit about NOR gates a while ago, but I never showed how I spec this transceiver because the 74 just means like it's a logic, the family, the TI logic family. 245 is the name of the 8-channel transceiver, non-inverting transceiver. But the AHCT, hold on. It is the AHCT actually all sort of stands for stuff. And you can't necessarily swap out different versions. The AHC is, I think, high speed, and A, I think, means it can run from 3 to 5 volts and can take up to, it can take voltages that are above the VCC if necessary. So it's got that, can go from 3 volt to 5 volts or 5 volts down to 3 volts. And the T is transistor level input. If you get the if you get the AHC version, that is CMOS, and when you add the T, it's transistor level logic, and I'll show you in the data sheet why you want transistor level logic. That's actually hat tip to Paul S from PJRC. You can get away with running the non-T version, but it is good taste, and it's the same price to use the transistor level logic version, because it does make a difference. You know, if your voltages are a little marginal, it can make a difference. Okay, so let's go to LaDigiKey.
That's the French site?
Yes, sorry. LaDigiKey.
Yeah.
And I want to look for a buffer transceiver. Receiver. I before E, E before I. Did I spell it right? Yeah. So there is a whole section called interface, drivers, receivers, transceivers. They're all kind of the same thing, kind of, sort of, maybe, you know, again, I happen to know that I want the 245 series, but I'm showing how you could kind of like reverse figure that out. Okay, so for this, it's going to be an active design, so I only want active parts. It needs to be small, so I only want surface mount, and I'm going to apply. Next up, I only want stuff that's normal stocking, and I'm going to, for now, just exclude marketplace products. So that just kind of reduces it. And then I thought I clicked active, but maybe I didn't. I'll say that the new thing where it previews the things for you before it does them has confused me a little bit. Okay. I think, oh, you know what? I'm actually in the wrong section. There are two places. I went to drivers and transceivers. I meant to go to buffers and transceivers. Silly me. Sorry. That was interface. See, you're learning something from me. I went to interface, drivers, transceivers. What I meant to go is logic, buffers, receivers, and transceivers. So, silly me. But now we're here. And yeah, now you're seeing there's 74 series logic here. So, yes. Okay, so again, I'm going to go for active. And I'm going to go for normally stocking. And I'm going to exclude marketplace. Okay, great. So next up, I want non-inverting. Inverting, of course, flips things over, but I don't want that. I want signal in to be signal out. So I'm going to select buffer and transceiver, both non-inverting. Exactly the opposite of what I just clicked, which is ironic. Okay, so next up I want surface mount. And now we're... So technically a transceiver, the data can go either way. So you could use a buffer. But in this case, one thing I want to do is I want, again, to have 8 bits of data. And it can be a little confusing, I'll say, because sometimes there's two things here. There is number of elements, and that goes from 1 to 8. And then there's number of bits per element, and that goes 1 to 10. And you might be like, well, how do I want 1 element with 8 bits or 8 bits with 1 element? You try both. In this case, I had already looked it up. So I want 1 element with 8 bits. Which is a little confusing. So let me apply that. Okay, so now we're seeing a lot of 245s, because that's kind of the classic part number for the 8-bit non-inverting transceiver. Okay, so next up, remember I wanted to have that small package. The TSOP was too big. So normally I'm not as picky about the package, but this time I'm skipping over all the TSOPs and the TFSOPs, and I'm going straight for the 20 QFNs. And I'll say there actually aren't a ton of QFN options, but the QFN, you know, it's going to be much, much smaller. It doesn't have legs. A lot of the 74 series logic, of course, started as DIP, moved to SOIC, then SSOIC, and then, you know, you can sometimes get it in VGA, or in this case, DFN. So last up, I'm going to do the voltage supply. Now remember, it's the microcontroller's 3 volts, but I want to output 5 volts. So what I'm going to do is I'm going to power the buffer with 5 volts. I feed it 3 volt logic. Whatever it's powered by is the output signal. So I'm going to make sure that this can be powered by up to 5.5 or 6 volts. And this is where it's like it gets really limited. So there's really only like a dozen options now. And then let's just look at the ones that are in stock. So now there's only 10. And I messed something up. Hold on. Okay. So now there's a couple different versions here. There's like the VHC, the AHC, the HC, the HCS, HCV, etc., etc. And what I'm saying is I'm going to be using the HCT. And the reason for that is if you go to the data sheet, and this data sheet covers both the AHC and the AHCT version. Again, HC, CMOS, HCT is transistor TTL logic. And if you look at the... Okay, this is the HCT 245. The high level input logic is 2 volts. You can see right here. And if you go up to the AHC, the non-T version, it's CMOS, so the voltage input level is going to be much higher. The requirement for it to register is high. If you power it from 5 volts, it technically wants you to give it at least 3.8 volts logic, which if you're running a 3 volt logic, you're not going to get. Now I'll say, because I'm a naughty person, and I'm going to get coal in my stocking, except I'm not, because I'm Jewish. But if I was, you shouldn't assume that your HC logic will be happy with the voltage lower than 3.8. The datasheet specs it at 3.8. It wants 3.8. If you're giving it 3.3, it's going to likely work, so like don't freak out. But the right thing to do if you're speccing the part, and it's the same price anyways, is to go for the HCT version, which has the TTL logic input, which means that the logic input level is the same no matter what the voltage is. And then maybe one day we'll cover the difference between CMOS and TTL logic. Trade-off, use a lot more power on the TTL logic input. So downside, but if you're driving 8 strands of NeoPixels from this board, you don't care about power because one NeoPixel uses more power than this transceiver. So not a problem. So this part is quite nice and better off, it's in stock. Best of all, it's in stock.
Yeah.
So I ordered a bunch of these. And there's a couple, again, there's like the VHCT maybe. There could be others that also have, can be driven off of 5 volts and can take a lower voltage, but I don't remember all of them. I do know that this one will work, so I'm happy to purchase it. And if it ever runs out of stock, I can always look at alternatives.
That's great search.
Where in the world is that part I need? The great search with DigiKey.
All right. I got to get you out of here, lady.
I know.
We've been on
I'm
trains,
gonna turn
planes, and
out to a
automobiles. So we'll see everybody during the week. Thank you so much for supporting this cool, interesting, weird art project we like to call Adafruit. We'll see everybody during the week. Thanks for joining us on Desk of Ladyada.
Don't
Bye,
forget,
everybody.
we still have pink feathers in stock.
We do.
So if you want to order from Adafruit, you want a free
This is it.
feather.
Get them, get them, get them. They're going to be awesome again.
They're going to be gone in like 2 days.
Yes. Bye.
Bye.